right, first off, I want to thank everyone for coming out this morning and watching these presentations. I know we all put a lot of work into it, so I'm hoping we can give you some entertainment and some information. All right, so today I'm going to be talking about the light spectrum of Kepler 75b. It's actually a star that was studied intensely by the Kepler Space Telescope, and it can tell us a lot of information about the star and maybe any planets about it. So I'm going to start off basic. What is the Kepler Space Telescope? So, the Kepler Space Telescope was launched on March 7th in 2009. It was part of NASA's Discovery program, and it was named after Johannes Kepler, who was a German astronomer and mathematician. He was also an inventor of a certain type of telescope. And his goal was to shed light on other solar systems, and in turn produce knowledge that we can use to better understand how the universe functions and our place in the stars. Its more express purpose was to study and look for planets that are in what's known as the Goldilocks zone, which is a certain distance away from its host star, where it can support liquid water, and in turn may support life. So this mission was originally set to run for about 3.5 years, but certain obstacles pushed that back, so it's been extended. In 2012 and in 2013 subsequently, there were 2 reaction wheels that failed, which meant that the spacecraft had to change how it took the data, and instead of its original purpose, had to be repurposed to study more on red dwarf stars. It's still operating, but it is running low on fuel, and its purpose has been changed. So this Kepler Space Telescope itself has a camera that's focused on one portion of space over a long period of time, and it takes a picture about every 30 minutes, and it measures the amount of light coming from every pixel in that image. So it measures the amount of light coming from each portion of space over a long period of time. With a camera of about 95 million pixels, they can get pretty accurate data. Results of the mission was actually a giant success, and in January of 2015, NASA announced that they've discovered over 1,000 confirmed exoplanets, with many of thousands of candidates still in the running. Many of those have been confirmed since then. These were found by using what's known as the transit method. So it would look at a particular area of space and zoom in on just one star, and it would watch for regularly timed dips in the light coming from that area. And if that was regularly timed and regularly spaced, they could assume that there was something transiting in front of the star blocking the light, and that was assumed to be a planet. Now you do have to be careful. There are false positives where in a binary star system where 2 stars are rotating around each other, if a dimmer star passes in front of a brighter star, it might give a similar look, but with further analysis and ground telescopes, you can actually determine if it is a planet or another star or another anomaly. There's many different types of stars, and all these stars can be classified by their light spectrum. There's RL-Lyra rotationally variable, which is important in this case, red and white dwarfs, and all of these have different functions. You can use them to study the distances in the universe, the time scales, how fast things are moving away and towards us, and all these different stars can be used for their express purposes. All right, so the Kepler Space Telescope was put in orbit around the sun in order to ensure a more continual picture, that it has less interruptions. But even then, as it moves from one side of the sun to the other side of the sun, it has to be recalibrated so that the picture that it's taking is still focused in the same area of the sky. And the way that this background light interacts with the sensors and the sunlight interacts with the sensors, every few hundred days, it does have to be recalibrated. So there's gaps in the data, and every fluctuation in the data has been tried to be accounted for by either hardware failures or background light. All right, so in our case, we're looking at Kepler 75b. So the NASA Exoplanet Science Institute examined this star, confirming an exoplanet with an orbital period and a specific transit time. The data was taken for roughly 1,459 days. About every 30 minutes, a picture was taken. There are gaps every few hundred days to readjust and recalibrate the camera. So this would leave gaps, and technical difficulties also left gaps in the data. So how did I analyze this? All right, so first we needed to stitch together this data in order to account for all the background differences in the light. So we imported the data into Excel using NASA's MAST program, database, and programs like 7-Zip and TopCat to extract the data. We then imported this data into Python as the light flux and the time, and arranged it into an array. And with over 70,000 data points, this actually was a great sample size. So this is what the graph looked like originally. You can see on the left is the light flux. or the amount of light coming at that time. And on the bottom, the x-axis, there is time in days. So as the days went forward, that is the amount of light coming from the star measured. So we stitched together this graph, and this is all relative to itself, and it formed this nice little arc. Each of these little bumps is about 372 days, or is represented by the orbital period of the Kepler Space Telescope around the sun itself. So that is the background light fluctuating. All right, so how did we analyze this? First, we ran a Fourier transform over the data set. So a Fourier transform, it's a mathematical method that analyzes a data set with evenly spaced data points, and it tries to reconstruct the previous graph you had just seen using sine and cosine functions. Now, this can tell you any repeating patterns in your data and how prevalent they are. So Python has a fast Fourier function algorithm, and we use that over our data set to see what information we can glean. All right, so when we run these transforms over the data set, you do have to be careful. There are a few pitfalls you can fall into. So we got reoccurring data points at 1/2 and 1/4 of the total amount of data points taken. So as we, here. So let me just further explain. In order to see which data points are legitimate or are important in making up the graph, we actually changed what portion of the data points we ran the Fourier transform over. So we ran it over the first half of the data points and the second half of the data points, and we saw which sine and cosine functions with specific periods were constant over those different sections. So when we did that, we actually found that there were only 2 that were constant, which was a 19.3 day period and a 37.4 day period. Now, the 19.3 day period, if you look at this graph right here, it's a zoomed in version of the stitched together graph. And each one of those peaks to the next peak is about 19.3 days. So that's where a rotationally variable star comes into play. And we can see that the star is rotating, and due to sunspots or other irregularities on the star surface itself, that can account for that fluctuation of light. 37.4 days was a little bit more unclear. I do believe that it was related to the 19.3 days, maybe in some of these little smaller fluctuations, but I can't say anything for sure. If you look at this graph, you can actually see the transits of the planet themselves kind of dipping down into here. So we decided to observe that a little bit more. So taking the Kepler data, we did fit parabolas into each of these transit dips and took the vertex of those parabolas to represent the center of the dip, or the center of the transit of the planet across the face of the star. When we did this, we then took the average of the time between each of these transit centers to find the average orbital time of that planet around said star. Our result came to about 8.88992 days, to which we compared against other previous published measurements in NASA's Exoplanet Archive. And when we did this, along with the uncertainty in values, we did see a match of within a second. This is just kind of a side note, the transit depth differences from the mean over time. So in this graph, the 0 on the y-axis represents the average transit depth of each of the transits using those parabolas. If it's above the 0, that means that the depth was deeper than it normally would be. If it was below the 0, it's a little bit shallower. So it varied similarly to the graph that was stitched together, but actually it more correlated to the graph that wasn't stitched together yet. So when there was more background light, the transit depth actually increased counterintuitively. Now, I can't say anything about this, and it is inconclusive, but I did think it was interesting and may warrant further study. So what next? What else could we glean about this planet? You can use the transit time to reconstruct how far the planet is from the star as a ratio of the orbital radius to the star's radius. Other stars and light signatures may be able to give you the mass of the planet or the radius of the star and the planet. And that can help form a more complete picture. This has led to a plethora of findings in the Goldilocks zone and some fascinating star-planet relationships. And that is all. Okay. An exoplanet is just a planet that is orbiting another star other than our own. So any sort of planet that's outside of our solar system or consists is in another solar system.
What flux did you eliminate in order to stitch the graph?
Yeah, so let me see if I can go back to this graph. So basically, I just took the difference in the ending of one data set and the second data set, and then just subtracted that difference. And then we went to the next one and subtracted both of those differences and stitched them together. So I just put them end to end.
It almost seems like the difference in the fluxes are like similar. Is
Mhm.
there like a specific place where those fluxes are originating?
Yeah. So as far as I could see, it would just depend on so when we did stitch them together, we did see this pattern. So I did believe that as it's rotating around the sun, that the sensor, as it's moved, is either getting more sunlight or less sunlight, and that would repeat every time that it goes around the sun in a regular pattern. Yeah. Any other questions? All right. And that is all? Yeah.